So this video is about how to graph rational functions. And when we graph rational functions, we need to really determine three things. The first is we need to determine, are there any restrictions on x? And this could come in the form of two things. There may be asymptotes, which we saw in reciprocal functions, or there may be something called holes. And we'll talk about what holes are in just a second. The second thing that we have to consider are the end behavior. What's going to happen as this function heads towards positive and negative infinity? In other words, when we're looking at the end behavior, we're looking at our horizontal asymptotes. When you did your worksheet, we talked about the different patterns that developed with horizontal asymptotes. And so I'm just going to summarize those here. So if you remember, if our n was less than our d, in other words, the numerator degree was less than the denominator degree, so in the terms of all reciprocal functions, then the horizontal asymptote would occur at y is equal to 0 all the time. The other thing that you should have found out is that if n is equal to d, that the horizontal asymptote occur when y is equal to the coefficient of the numerator over the coefficient of the denominator. So for example, in this case, if I had the function y is equal to x cubed plus 3x squared plus 7, and I'm dividing that by 2x cubed plus 9x, something like that, notice that both the numerator and the denominator are of degree 3. So in other words, the numerator equals the denominator. So therefore, I know that I'm going to have a horizontal asymptote when y is equal to the coefficient of the numerator, which is 1, over the coefficient of the denominator, which is 2. So we always look in this space right there. Okay, the third thing that you would have figured out is if n is greater than d, then we're going to have no horizontal asymptote. What we are going to have is something called an oblique asymptote, potentially, and we'll talk more about oblique asymptotes later. Okay, but if the numerator is greater than denominator, for example, in the case where y is equal to 3x to the 4th plus 7 over 2x cubed minus 1, because the numerator is a greater degree than the denominator, then there will be no horizontal asymptote. Okay, let's keep going. We need to know the restrictions on x and the end behavior. And what these two things are going to do for us when I calculate these two is these are going to set up what we call our fences. Fences are, but the third thing we need to know are some points. And they're going to occur between the fence boundaries. So some of the points I might want to consider are my x and y intercepts, because those are the easiest, but sometimes they don't give us enough information, and so some other things that I might want to consider, or I might have to look for some other points if necessary. Okay, so that's my plan. I want to find the restrictions on x, the end behavior, and some points if necessary. Okay. The function f at x is equal to, let's go, x minus 2 over x squared plus 3x minus 10. That's what we're going to look for first, is our restrictions on x. And in order to find the restrictions on x, I need to know what values of x would cause the denominator to equal 0. And so in order to do that, my first step is going to be to factor. So the numerator doesn't factor out. The denominator, I got a simple trinomial here, so what multiplies to negative 10 and adds to 3, so that would be x plus 5 and x minus 2. Okay. So recognize that I've got two different factors of x down here. So there's two different values of x that could cause the denominator to equal 0. X could equal negative 5, and that would cause this factor to equal 0. And make it equal 0, I'd be dividing by 0, and we can't do that. Or x could also equal 2. Now, the question we have to ask ourselves, are both of those asymptotes? No is the answer. And look why. Notice that the top is a factor of x minus 2, and it matches the one that's on the bottom. If I was going to simplify, and I cancel both those out, then the simplified version of what I'm going to graph is 1 over x plus 5. However, x still can't equal negative 5, and x still can't equal 2. The graph that I'm going to graph, though, is this simplified version, and it doesn't actually have the factor of x minus 2 in it. So the 2 is not an asymptote. The 5 is going to be a vertical asymptote at x equals negative 5. The 2, because it got canceled out, we're going to write is as a whole at x equals 2. Is the function the simplified version of what I'm going to graph? That's what I want to graph. All right, so now I know my vertical asymptotes. That's the first step. The second thing I need to do is I need to determine my horizontal asymptotes. And that's going to tell me my end behavior. So my horizontal asymptotes, I look at my numerator degree and my denominator degree. My numerator degree in this case is 1. My denominator degree in this case is 2. And since my numerator is less than my denominator, then therefore I know I have a horizontal asymptote at y is equal to 0. Okay, so here's my x-axis, here's my y-axis, and I have a horizontal asymptote where y equals 0. So that's right along my x-axis. And I have to label it as y equals 0. Okay. I also know that I have a vertical asymptote at x equals negative 5, which is about here. I need to label it x equals negative 5. Okay. Okay, so next that I have to do is, so I found my fences. The next thing I have to do is to find some points. So I'm looking at different sides of my asymptote. So let's look in the left-hand side of my vertical asymptote and find a point there. If negative 5 is my asymptote, let's see what happens at negative 6. So I go back into my simplified version of my function that I'm graphing, and I say, hey, what happens when x is negative 6? When x is negative 6, is going to be 1 over negative 1, which is going to just be negative 1. So at negative 6, I'm going to have the point at negative 1. So this is the point negative 6, negative 1. And then, like we said, our points like to hug our asymptotes. So this is going to get as close as it can to y equals 0 without touching, and this is going to get as close as it can to x equals negative 5 without touching. And this is what was happening on the left-hand side of the fence. Let's see what happens on the right-hand side of the fence. On the right-hand side of the fence, let's see what's happening when x is equal to negative 4. When x is equal to negative 4, my function is going to be 1 over negative 4 plus 5. Negative 4 plus 5 is equal to 1, so my function is going to be up here at positive 1. Okay, so this is going to be at negative 4, positive 1. And again, my function is going to hug this asymptote, and it's going to hug this asymptote. Oops. It went crazy. And it's going to hug that asymptote as well. And this is a graph of my function. The only thing we haven't used, though, is this x equals 2. I said that there was a hole whenever x is equal to 2. So what is going to happen here, let's go get my eraser, get rid of that little arrow, is as I'm approaching 2, well, as soon as I get to x is equal to 2, this function no longer exists. So I put a big hole there, but then it keeps going. Okay, in example 2, we are going to graph the function f at x is equal to 2x squared minus 8 all over x squared plus x minus 2. Okay, same steps. Let's determine what our vertical asymptotes are. A difference of squares going on here, x minus 2, x plus 2, and x plus 2, x minus 1. Okay, once it's in factored form, now I can determine what the restrictions are on x. So therefore, I know that x can't equal negative 2, but this is going to be a whole. And x can also not equal positive 1, and that's going to be a vertical asymptote. All right, so that's part of my fences. The second thing I need to do is look at any horizontal asymptotes. So the numerator equals the denominator. And whenever we had that, we had a horizontal asymptote at y equals the coefficient in front of the numerator divided by the coefficient in front of the denominator. So in this case, I have a horizontal asymptote at y equals 2. Some points. So let's take a look at our x-intercepts. Our x-intercepts we calculate by setting y equal to 0, right? So let's go back into the original function and let's make y equal to 0. But I want to calculate my x-intercepts of the simplified function. So the simplified function is 2x minus 2 over x minus 1 because x can't equal negative 2. We've canceled that out. So I'm going to calculate my x-intercepts of the simplified function. Okay, so my x-intercepts, I set y equal to 0. So what I've got then is 0 is equal to 2, x minus 2 divided by x minus 1. If I want to solve for x, I'm going to multiply both sides by x minus 1. And so I'm going to be left with 0 is equal to 2. And I'm going to simplify over here, x minus 4. Solve for x, so I'm going to have 4 is equal to 2x. So x then is equal to 2. So therefore I know I have an x-intercept when x is equal to 2. And that'll help me with a point. Let's calculate our y-intercept. Our y-intercept, we do the opposite. We set x equal to 0. And so when I go back to the function that was simplified and I make x 0, I'm going to have my y-intercept is going to equal 2 bracket 0 minus 2 over 0 minus 1. And we simplify that. 0 minus 2 times 2 is going to be negative 4 over negative 1, which is going to be at positive 4. And sometimes these points can help us. Okay, so now that I have all this information, let's go ahead and graph what at x equals 1 and a horizontal asymptote at y equals 2. Okay, the other thing that I know is that, the other two things that I know is that I have an x-intercept at x equals 2. So an x-intercept at, there's x equals 1, here's x equals 2. And I have a y-intercept at 4. So 2. We know that our points hug our asymptotes without touching them. Okay, and there's our function, except for the one thing that we forgot. If you go back up here, don't forget that we had this hole. Go back down here, grab our eraser, and at x equals negative 2, which is about there, I'm going to put a hole. That's at negative 2, because there's no definition of the function at that point.